Now I'm going to continue our exploration through the world of mathematical proof by induction, and I'm going to look at what I think is the easiest type of induction question that you can get, and that is a question on matrices. Now, a lot of people, I think, just look at the matrices and think, oh my word, that looks ridiculously nasty. But actually, it's not. It's the easiest question you can get in terms of, because basically it's the same recipe. For every single induction question, it's the same recipe which is down here. Okay, and I've said before that with induction questions, the algebra can get really, really involved. Okay, and sometimes it can be difficult to lose track of where you're going because the algebra is so kind of involved. Whereas with matrices, the hardest the algebra pretty much gets is multiplying matrices together. Okay, it's not difficult algebra at all. So I think the best way of trying to explain this is by actually just looking at an example and talking you through it, because if you can understand this example, it'll be pretty much exactly the same question, just with different numbers. And interestingly enough, from the past 5 years, for Edexcel FP1 paper, I could only find one question, and even then it was half a question at that. It was part B of the question. So I'm looking at 9 part B of the June 2013 Edexcel FP1 paper. Okay, and again, you're always going to have a matrix raised to some power is going to equal another matrix, and you're going to have to prove that, and that other matrix will always have elements involving the power which you're raising it to in it. Okay, so let's just remind ourselves of the steps. I mean, you're probably familiar with this. First step is the base case, so we stick in m equals 1, and we show left hand side equals the right hand side. Simple as that. Anybody can do that, quite frankly. So that's an easy mark which anybody can get. Second step, assume some general case is true. So we choose a case, k, okay, general case k, and we assume it's true, and we come up with an expression for that case. And then our third step is we basically try and show that the k plus 1th case, the m equals k plus 1, depends on k being true. Okay, so we have to basically use our expression for k, our m equals k expression, in our m equals k plus 1 expression, and kind of show that it works. And then the fourth and final step is just inclusion, which is just saying the right things in the right order. So here's our matrices. Our first step, again, I'd always encourage you to write down the steps in the exam, because if anything, it shows to the examiner that you've got a logical way of thinking. You're thinking kind of in this logical way. Our first case is our base case, which is first step is our base case, which is m equals 1. So let's have a look at this. 3 minus 4 minus 1, that's the left-hand side. So our left-hand side, I should write down left-hand side to the power of 1 is equal to this. Left-hand side is equal to this. And our right-hand side is equal to... Now be careful here, because the temptation is just to evaluate this in your head. Just stick m equals 1 in here. I don't think the examiner would have an issue with it if you just wrote down 3 minus 4, 1 minus 1. But because you'd just be evaluating this in your head and you get that, I'd recommend to write down intermediate step to show that you've actually tried to input 1 in here rather than just copying this down. You know, they could accuse you, the examiner could accuse you of just copying this down again. So you'd have 2 times 1 plus 1. You'd have 1. Here you would have minus 4 times 1. And here you'd have 1 minus 2. And then I'd write that out again as 3 minus 4, 1 minus 1. Be careful when you're writing matrices as well. Look, make sure there's a gap between the elements. Before I just wrote down a big 4 and it looked like 3 minus 4. Okay, so we've shown that because left-hand side equals right-hand side, therefore base case is true. Our next step is our assumption step, and that is our m equals k. Okay, so we have got 3 minus 4 on the left, 1 minus 1 to the power of k. That's to the power of k. That's our left-hand side, and that's going to be equal to 2k plus 1 minus 4k, k, and 1 minus 2k. All I've done there is I've just replaced m with k. Okay, and what we have to do is assume m equals k is true. Okay, so assume that this thing up here is true. Okay. Our next step is our inductive step. So we now try and link this back to we try and link m equals k plus 1 back to our m equals k. So we want to come up with an expression for m equals k plus 1. So we've got 3 minus 4, 1 minus 1 to the power of k plus 1. Now look, here we've got a matrix A, and we've raised it, we've raised it to the power of k plus 1. Well, just by indices, the indices still work with matrices. This is the same as saying A to the power of k times a to the power of 1. Okay, or I'm actually going to do it the other way round. I'm going to do a to the power of 1 times a to the power of k. It doesn't matter, it's just the way which I want to do it. Okay, because it's a square matrix, it will still come out the same. Or because the matrix is the same, I should say, it will still come out the same. It doesn't matter which way around you do it, so don't worry about matrix multiplication in this question. So I'm going to now write this out as a to the power of 1, which is 3 minus 4. So it's this matrix to the power of 1, 1 minus 1, times this matrix to the power of k. So 3 minus 4, 1 minus 1, that's all to the power of k. Okay? And I also know that this matrix here to the power of k is equal to this matrix up here. I've just worked that out. I've just come up with an expression for this matrix to the power of k. Okay, so this now is equal to, actually I'm going to write it underneath here, this matrix here is equal to 3 minus 4, 1 minus 1, times by the matrix 2k plus 1, minus 4k, k, and 1 minus 2k. Okay, so I've just simply replaced this matrix here with the expression what I know this matrix is equal to, which I worked out before. Because again, I'm assuming that is true. Okay, so I've now linked back this matrix to the previous case, but I also know that this matrix here is equal to the thing which I was given to in the thing which I was given to in the question, replacing m with k plus 1. Okay, so in other words, 2, we had an m here, so it's now going to be k plus 1, and we had in this element we had minus 4m, so it's now going to be minus 4k plus 1. Again, use brackets whenever you make a substitution. We're making a substitution for k plus 1, replacing m with k plus 1, so you always use brackets. And then we got 1 minus 2k plus 1. That just makes sure that you don't make a mistake by using brackets. Okay, so we now need to basically show that this thing multiplied out, I'm going to actually simplify this a little bit further, so 2k plus 2 plus 1 is going to be plus 3. Here I've got minus 4k plus minus 4, yeah? Then this is going to be k plus 1, and this is going to be 1 minus 2k minus 2, so I'm going to end up with minus 1 minus 2k. Okay, and now, what's going on? And now we have got to basically show that this thing up here is equal to this thing here. If we show that, then we've shown our inductive step is true. So we basically need to multiply this matrix out here, and we need to make sure that it is equal to this thing here. So in other words, 2k plus 3 minus 4k minus 4, k plus 1 minus 1 minus 2k. So that matrix there has got to be equal to this matrix up here. This matrix up here multiplied out. So 3 minus 4 minus 4, 1 minus 1 times by, what have we got, 2k plus 1 minus 4k, k, 1 minus 2k. So matrix addition, matrix multiplication rather, not addition, matrix multiplication. 3 multiplied by 2k. Write all the stuff out for your own sake, okay? I can't do it easily in my head. So 3 multiplied by this thing. So we've got 3 multiplied by this thing, 2k plus 1, minus 4 times k. Right, and that goes in the top left-hand element. And then in this top right-hand element, we've got 3 multiplied by minus 4k, multiplied, minus 4 times this thing, 1 minus 2k. Okay, and then in this element down here, we've got 1 times this thing, which is 2k plus 1, minus 1 times this thing, minus k. And then we've got 1 times this thing, which is minus 4k, minus 1 times this thing. 1 minus 2k. Okay, and then we just work this out. Hopefully it works out okay. So we've got 6k plus 3 minus 4k. And then in here we've got minus 12k minus 4 plus 8k. Careful the double negative there. And then we've got 2k plus 1 minus k. And we've got minus 4k minus 1 plus 2k, double negative. Okay, and then we just need to simplify that down. Hopefully it falls out. So we've got 6k minus 4k, that's 2k plus 3. And then here we've got, what's this? This thing here is minus 4k minus 4. And this thing here is k plus 1. And this thing here is, what's this? Minus 2k minus 1. Okay, and that is the same as that. This thing here is the same as that. So therefore we've shown that k plus 1 is true if k is true. Right, so we've now shown left-hand side equals right-hand side in that thing. So we've shown that m equals k plus 1 is true only if m equals k is true, because we've used m equals k in our m equals k plus 1 example. Okay, and now our conclusion, final thing. Notice that the algebra wasn't that hard there. The hardest thing was just multiplying out matrices, which I think you could do absolutely fine, and then basically just expanding and collecting together like terms. It's as easy as that. No, things which you've been doing since GCSE, quite frankly. You probably do it in your sleep. So the conclusion step is m equals k plus 1 is true if m equals k is true. Okay, and since m equals 1 is true, then it's true by induction for all m greater than or equal to 1, or all m which are positive integers. Okay, simple as that. So yeah, like I say, matrix examples, really easy algebra. The hardest thing is multiplying matrices out, which, as long as you're getting good at that, you have to be able to do that for the exam, and you get asked it in other questions as well. So as long as you can do that, you'll be absolutely fine.